Do we need the music? No. Okay. Here, we'll go back to just like there. Okay. What type of bond is that? That is a covalent bond between two hydrogens. Thank you. In other words, hydrogen has a full valence shell. Yeah. Why do they form double bonds? They have 2 unpaired electrons on their outer shell. They've only got 6 electrons. Yeah. What do you think will happen if we put a hydrogen and an oxygen in a box together? Nothing. Let's see if you're right. Ooh, you guys were right. Nothing. Okay, so on page 10, I think it's number 1, it says, at room temperature, what happens when you place an oxygen and molecule and a hydrogen molecule in a box together? What do the molecules do? They bounce around and do nothing. So that's question number 1 on page 10. They bounce around and do nothing. Okay, so B, what happens when you apply heat to the gases with the flame? They speed up, they crash, and they bust apart. They speed up, they crash, they bust apart, or break apart. Bust apart must be like an Australian thing. I think this guy's Australian. No, I actually got an email from him because I said his videos were really good and he should do more of them. And then he had like some resource, and I'm like, "Do you have more?" And he's like, "No, not yet." I'm like, okay. This is not Tyler. No. And he actually made these videos for elementary school students. But they're pretty cool. Okay, so number 2, why did the flame make a difference? The heat made the particles move faster. Now when the particles collide with the walls or with each other, they break apart. I don't know why I left such a big space for that. They break apart. When atoms are on their own, this is number 3, when atoms are on their own, they are free to bond with other atoms. And you'll notice that we got water here, but would it be possible for them to come back and join with their original partner? Yeah, absolutely. Okay, but it's not as interesting if that happens, so we're going to look at what happens if they become water. What happened here? What happened to this poor little oxygen, or this poor little oxygen here? Well, it's got some bonds, but it doesn't have any bonds, but it has bonding sites. Did it find anybody to bond with? No, it just got left over. Poor little sad little lonely little oxygen. Okay? So why can't that oxygen atom join up with the water molecule? Why does the water say, no, I'm done, I'm finished, don't want you? Yes? Yeah, the water molecule, the hydrogen and oxygen's valence shells are already full. So that's number 4. Why can't the oxygen join up? Because the valence shells in water are already full. What are we going to end up with if we have an extra H2? We'll end up with 2 water molecules. Yeah, let's take a look. How do we know we had a chemical reaction? Question 6. A new substance was formed. What do we call those things that we have at the beginning of a reaction, before they have reacted? We call them the reactants. That is question 7A. So you are going to draw what happens when the flame is applied. You end up with 4 separate hydrogens and 2 separate oxygen atoms. This doesn't happen at room temperature because there's not enough energy. Sorry, you had a question. No, okay, never mind. In grade 12, we'll spend a lot of time talking about the activation energy, and that's the energy that you need to break those molecules apart into atoms. They cannot react with each other unless they are broken apart. So that match provides the activation energy that breaks the atoms apart, that allows them to form new bonds. Okay. All right, we are now on page 12. What substances are present? What are the substances present after the reaction called? The water, what do we call that? The? Nope, that would be if we dissolved them. So we have the reactants, they react, and we get the... Does it start with an R? No, it starts with a P. Products, yes. Okay, so those are the products. Because they're produced. Okay, so you guys, I did not leave you space to rate this. I don't know what's wrong with me, but at the bottom of page 12, you can kind of work it around where it says the energy required to break the bonds in the reactants is called the activation energy. So you could write signs of a chemical reaction. And the first two are called color change and a precipitate. Did I? Page 11? I don't know. There's like 6 or 7 of them though. So anyway, write it wherever you want it. I will fix that for next year. So we have color change, we have a precipitate. And if you guys are wondering what a precipitate is, I want you to watch. Clear colorless liquid looks like water, yes? Clear colorless liquid looks like water, yes? If you blink, you will miss it, so don't blink. Here we go, 5, 4, 3, 2. Whoa. That is a precipitate. Is this clear or is it cloudy? Cloudy. In fact, it's very cloudy. And what makes it cloudy? What does there have to be in order for it to be cloudy? Cloudy means that the light is coming in and it's bouncing back. That's why it's not going through. That's why it's not transparent. What is it bouncing off of? What is the light bouncing off of? You got to remember way back to that little solution lab we did way at the beginning of semester. Sorry? Molecules. Molecules are too small. It'll go right past a molecule. Light will go right past a molecule. All right, well, I'll let you guys think about that. We'll come back to it tomorrow. Okay? Okay, so you'll want to add those 3 in, bubbles of gas, a new smell, a solid dissolving. And like I said, I didn't really leave a good space for this. Write it anywhere you want to. So different bonds have different amounts of energy. So you start with some bonds that have a certain amount of energy, and you finish with different bonds that have a different amount of energy. So either you're going to start with lots of energy in the bonds and go to a small energy in the bonds, in which case energy has to be released. Or you start with a small energy in the bonds and you go to a bigger energy in the bonds, in which case energy had to have been absorbed. We'll talk a lot about that in section 6.4. So if that just went right over your head, don't worry about it, okay? Okay, heat, light, and noise are forms of energy. So heat, light, and noise can be signs of a chemical reaction. Okay, so can you guys think of a chemical reaction where you can feel heat coming out of it? Fire, exactly. If you have a fire, that's a reaction where the heat is coming from the reaction, it's coming out into the surroundings, into the environment. If you've got like a fire going, you can be standing back here and you can feel that heat coming out. Okay, it's making the molecules of the air move faster, and those molecules of the air are bashing into the molecules of your palm, and it's making the molecules in your palm move faster. And it's that faster movement that feels warm, that causes the temperature to go up. Okay, now this sometimes messes people up because they think, oh, the system absorbed energy. It should get hotter because they're like, it has more energy, it absorbs heat. But the trick is that it pulls that kinetic energy out of the surrounding. So if you've got your, let's say we had a beaker, let's say there was a reaction happening in here and I put my hand on the side and it felt really cold. It feels cold because the molecules in my hand are slowing down. Why are they slowing down? Because there's less kinetic energy. Why is there less kinetic energy? Because the reaction is sucking kinetic energy out of my hand and it's turning it into potential energy in the bonds. Okay, so the trick is when we say something absorbs energy or it absorbs heat, it's not just absorbing it, it's absorbing it and turning it into potential energy. So it's no longer heat energy, now it's potential energy. Okay, so that's why sometimes people are like, it absorbed heat, it should get hotter, but it's absorbing heat and turning it into non-heat energy. So this is circled right now. Okay, there's supposed to be a bubble sheet that's not working, and I'm just marking a few of them. It's only like third mass production. Okay. What do we call that kind of a reaction? That is called, the other one was exothermic. This one is called endothermic. Okay, and we are now, I got to pull up your guys' thing here. There we go. We're on page 13 now. No, 6.1. What? There we are. Okay. 13. Okay, so question number 10. The video lists solid dissolving as being a sign of a chemical reaction. Is it always true that a solid dissolving is chemical change? Are we always getting a new substance? No, why not? When could we have a solid dissolving and we don't get a new substance? If you have sugar dissolved in water, anything like that. Okay, so if we have a salt dissolving in water, we start with NaCl, we finish with NaCl. These are the same. Okay, the only thing we have changed is we have gone from being a solid to being aqueous. We have had a change of state. And changes of state are physical changes. Okay, there's no new substance. But what if we have iron plus hydrochloric acid, and then we end up with iron chloride and hydrogen gas? Do we have new substances being formed? Yes. We started out over here with iron, which has a 0 charge. Any element by itself, unless it has a charge written at the top, in which case it's an ion. If it doesn't have a charge written at the top, its charge is 0. Okay, so that iron is 0. That means that this H2 over here also has a charge of 0. It's an element, it's on its own, it doesn't have a charge written beside it, so it's not an ion, it is just 0. How about the H in HCl? What is its charge? +1, yeah. So we have H+, and our iron here. What is the charge of iron in FeCl2? 2+. So you can see we started with iron 0, and it became iron 2+. We started with hydrogen positive, and it became H2 neutral. So we have electrons transferring from one species to another species, and that's always a sign of a chemical reaction. And if the word species sounds strange, that's what we call chemical things. Okay, get used to it, because in Chem 12, we talk about chemical species all the time, and it's just a fancier way of saying it's a chemical thing. Okay, it's a chemical species. Okay, so new substances, therefore chemical reaction. Ooh, and I'm going to show you my abbreviation for reaction. Do you know it yet? Have I shown you? RXN. Reaction. Because reaction is a long word, and we write it all the time. RXN. Reaction. Okay. Ooh, anybody happen to know what type of reaction this is? It is a single replacement. The iron is coming over here and it's kicking out the hydrogen and it's taking its place. We have a single replacement. Okay. The video lists bubbles of gas as a sign of a chemical change. Is there a case where we can have bubbles of gas and it is not a sign of a chemical change? When do we get bubbles and there's no chemical change? When you heat up water, when you boil something. Okay, so when you boil it, that is not chemical. So that would be like this one here. We have water, which is a liquid, goes to water, which is a gas. Those two are the same. Therefore, this is a physical change. And just so you know, liquid to gas, if we have to heat it up to do it, that is called boiling. What do we call it if we go liquid to gas just like at room temperature? Evaporation. However, if you take some baking soda, which is sodium bicarbonate, and I actually had experience with this weekend. I had a drain that was running really slowly, and so I stuck like a skewer down there and I fished around, and then I put a plunger in and I plunged it and a whole bunch of black gook came out, but it was still draining really slowly. So what I did then is I took some sodium bicarbonate, some baking soda, and I poured it down the drain, okay? And then I took some acetic acid, which is vinegar, and I poured it down, and guess what I got? I got carbon dioxide, I got water, and I got NaCH3COO, sodium acetate. What part of that would be useful to me in trying to dislodge all the stuff in my drain? Bubbles. Yeah? So it's like bubbling like mad, okay? Also the fact that there was acid down there, that can't have hurt. You know, it's a not very strong acid. Vinegar is kind of a weak acid, but it helped as well. And then the kicker, what I did afterwards was after I'd let it bubble and I kept pouring vinegar until it stopped bubbling, and then I rinsed it down. And then I got 2 dishwasher, like little, like, you know, those little packets, like a pod, dishwasher pod. I put them in there and I poured boiling water down it. Runs clean now. I did not have to take apart the drain. I'm not strong enough to do that. I don't know. It's just too hard. Okay, anyway, so we get bubbles. We had a gas, and that is chemical. There's a whole bunch of new substances. So if you ever need to clear out a drain, now you know how. The plunging part is really gross, though. The stuff that comes out of there, it's like black and like solid and absolutely disgusting. Oh, okay. Now, if the bonds in a reaction release energy, this energy moves into the surroundings. And by surroundings, we mean the beaker, your hand, the water, whatever happens to be around those reacting particles. And those things get hotter. And so what happens to the temperature? Does it increase or decrease? Temperature increases. And a reaction that releases energy is called exothermic. Exo, exit. Thermic, heat. Exit, heat. Heat is transferred to the surroundings. If the bonds absorb energy, this energy is taken out. Yes, it is endothermic. It is taken out of the surroundings and it cools them down. And if it's cooling them down, this shows a decrease in temperature. And a reaction that absorbs energy is called endothermic. And you can kind of think of that like enter, endo, enter, heat. And remember, why does that heat that enters not make it hot? Why doesn't the temperature go up? The heat enters, and then what do the chemicals do? They suck it up and they store it in their bonds. Okay? The heat is movement energy. Okay? Oh, they're moving so fast. And all of a sudden that energy goes into making this really stable bond. What happened to the amount of motion? Is there more motion or less motion? Less motion, because now the energy is stored energy instead of movement energy. Stored energy, movement energy, stored energy, movement energy. Hot, cold. Okay, where to go? Pen. My pen is gone. There it is. Okay. Whew. All right. This is just a little blah, blah, blah about that. Like I said, we'll talk more about that in 6.4. What is the energy required to break the bonds in the reactants called? What do we call that energy? The activation energy. Okay. Very good, very good. And I think that's it for this page. Yay! Okay, 6.1.3. 6.1.c. What symbol do we use to separate the reactants from the products? What goes in between the reactants and the products? Arrow. What do we write instead of and in between chemicals? We write a plus. To accurately represent the number of particles taking place, we often write a number in front of the molecule. So for example, we might write 2NH3. What is that number called? That is a coefficient, yes. Now I'm going to write down a little example here. N2 plus, and I'm going to leave a space, H2 gives NH3. This is the formation of ammonia. Okay, this is ammonia. And I'm going to give you like a little preview of a trick that I'm going to give you for balancing. Anytime you have an odd number and an even number of a particular atom, we have 2 H's and we have 3 H's. You can find the lowest common multiple of those two numbers. What is the lowest common multiple of 2 and 3? 6. So what I'm going to do is I'm going to put a 3 in front here because that's going to give me 6 hydrogens on the left. And I'm going to put a 2 in front here. That's going to give me 6 hydrogens on the right. Are you with me so far? Okay. Now, how many nitrogens do I have on the right-hand side? I got 2 and I got 2. Look, my reaction is balanced. Okay, so that's one little trick that makes some balancing easier. Okay. Does the number of molecules stay the same before and after the reaction? Let's take a look at this reaction. How many molecules in the reactants? How many N2 molecules? 1. How many H2 molecules? 3. How many all together? There's 4 molecules in the reactants. How many molecules in the products? 2 molecules. So when a reaction occurs, do we conserve the number of molecules? Does the number of molecules have to stay the same? Did it stay the same? We went from 4 to 2. So is the number of molecules conserved? Does it stay the same? No. But that's for molecules. How about the number of atoms? Well, let's look over here. How many N's do we have in the reactants? We have 2 N's. How many H's do we have in the reactants? 6. How many N's do we have in the products? 2 N's. And 2 times 3, how many H's in the products? We have 6 H's in the products. So have we conserved the number of atoms? There's 8 atoms here. And there are 8 atoms here. Did we conserve atoms? Yes. So was the number of atoms conserved? Did it remain the same? The answer is yes. How about the atoms of each type? Did each type also remain the same? Yeah, the N atoms stayed the same, the H atoms stayed the same, so the answer is yes. How many people have heard of the law of conservation of mass? Have heard of it? About half of you, okay. Anyone know what it is? Matter cannot be created nor destroyed, yes. And what that's saying is you cannot take an N atom and obliterate it. It cannot just disappear. That's why you have to start with 2 atoms, finish with 2 N atoms. You can't have a different number at the beginning or the end. Matter can only be transformed. That's why we don't necessarily have the same number of molecules, because we just have different molecules. Okay, what's a word equation? It's where we simply use words. Okay, so when we write a word equation, we would have the actual word hydrogen plus oxygen gives water. When we write the formulas, that's called the formula equation. And here we have our equation. Is this a balanced equation? No, because if we look, we've got a little 2 here. That tells us we have 2 H atoms. We have, on the other side, we also have 2 H atoms. That's nice. That looks good. But we have 2 O atoms on the left, and we only have 1 O atom on the right. How do we fix that? What do we use? We have to have the same number of atoms of each type on each side. We use, actually, before we do that, can I do it? Can I fix it by writing a subscript there? No. Why not? Yes. Number one, the charges are unbalanced, but number two, it's a totally different substance. You cannot change the substance. Not water. So you cannot change what you're actually producing. Instead of using a subscript, how could we get 2 oxygen atoms on the right-hand side? We would need to use coefficients, okay? How can we fix it? Use coefficients. How do we do that? Well, let's go across to the other side. Here we have, we're going to put a 2 in front here. Okay, so we have now put a 2 in front of the H2O. We're now on our next page. That gives us now 4 hydrogens. Uh-oh. But I do have 2 oxygens. That's good. Yay. Okay, I got 2 oxygens, and I got 2 oxygens. That's good. But unfortunately, I only have 2 hydrogens on the left-hand side. How could we fix that? Yes. Put a 2 in front of the H2. God bless you guys for participating. I literally, in the last block, I was like, okay, when you guys decide you want to answer me, wake me up. And I just sat there with my eyes closed for God. It must have been about 2-3 minutes. It felt interminably long. It was so horrendous. That's why I'm recording this one and not just going with the lesson from the last one, because it was really awkward and weird. Okay. By balancing the O atoms, we have unbalanced the hydrogens, but we can balance it by putting that 2 there. So always balance using coefficients, never change the formula. 2 things that students confuse. I noticed this in my grade 12 a lot because, and it makes sense why you would confuse them. In math, in physics, you probably use the words equation and formula kind of interchangeably, like they kind of mean the same thing. Yeah? But in chemistry, the formula refers to a chemical species. Oh, look, there we go. There's our chemical species again. So this is a formula, NO2. O2, that is a formula. Fe is a formula. It is just the letters that you use to write a chemical. Yes? That's a formula. But the chemical equation is where you have your reactants, and you have a plus sign in between them, and you have an arrow, and you have your products, and you put a plus sign between them, and that is a chemical equation. And I have had students in Chem 12, there's a thing that says give a formula of an amphiprotic anion. And they proceed to write an equation and get very confused because they don't know what to do with it. Because really they were just looking for a formula and they're trying to write an equation, and that confuses them. And then they spend a lot of time on what should have been a 1-mark question. right? Like a little gimme. Oh, look, do not use an equal sign. It's so easy to do. I know it's just like, using the word equation wrong, because in math, it's all equals all the time. Even when we're doing moles, it's all equals all the time, right? No, in a reaction, it has to be an arrow, okay? Just for future reference, an unbalanced equation can be known as a skeleton equation. And now we are going to write the word equation, then the skeleton equation, and then the balanced equation for the following. Aluminum metal combines with bromine to form aluminum bromide. Let's do the word equation first. Aluminum. How do I write reacts with or combines with? Plus. Bromine. To form, what do I write? I write an arrow. Aluminum bromide. Thank you very much. Okay. Now let's write our skeleton equation, which is with the formulas. Aluminum is just Al. Now, I'm not going to get too wound up if you get the states or not, but I'd like you to try with things you should know. You should know the state of aluminum at room temperature, because you have lots of experience with aluminum, yes? It's a solid. I mean, if you look at your aluminum foil, you're not like, is it a gas? Right? You're not like, oh, liquid, that'll store my sandwich nicely. No, it is a solid, okay? So when you know them, try to put in the states. Bromine. Anyone know anything about bromine? Yes. It is diatomic, so it should be Br2. Okay, so anytime you have a diatomic, make sure you write it that way. And anyone know the state of bromine? It's actually a liquid at room temperature. It's one of only two liquids, mercury and aluminum. Or not mercury and aluminum, mercury and bromine are the only two liquid elements at room temperature. Now, bromine is close to its boiling point. It doesn't take too much to get up there, but it is a liquid at room temperature. And then we have our arrow. And I'm going to show you the most common mistake that people make. What is wrong with that? Yeah, the charges aren't balanced, okay? Lots of times people will be like, oh, it's diatomic, so it has to be diatomic. No, it's only diatomic when it is on its own. Diatomics are only diatomic when they are on their own. So don't try and make it diatomic in there. Try to balance your charges. Al is 3+, bromide is negative, so it should be AlBr 3. I'm going to just give you a little quick introduction to balancing. Probably you could do this without like knowing how. This is a pretty easy one. One way of doing it that some people like to use, they like to say, I've got 1 aluminum on the left and I have 1 aluminum on the right. I have 2 bromine on the left and I have 1 bromine. No, I don't have 1 bromine. I have 3 bromines on the right. This helps people keep track. You are not required to do this, but if you like it, you can. Now, do you see that we have a 3 and a 2? Odd and even. If you have odd and even, use the lowest common multiple. What is the lowest common multiple of 2 and 3? 6. Okay, so I don't want 2, I don't want 3, I want 6. So what I'm going to do is in front of my BR to get 6, I'm going to put a 3, and that's going to change this to a 6. Do you see how you can keep track of your changes down in your little chart below? Okay. And if I want 6 on the right, I am going to multiply this whole thing by 2, which changes the bromine to a 6, but it also changes the aluminum to a 2. So do I need to do anything else to finish balancing this? Yeah, we need to put a 2 here in front of the aluminum, and that means we have 2, 2, 6, 6, check, check. Everybody's balanced. Okay? And I think that was as far as I got with my other block, and we have 10 minutes left. So, did you want to watch the first part of the little Tyler video so you don't have to do it for homework? You're like, no, I want to do Tyler for homework? Up to you. Page 22, the one I was like so mad that you didn't do, but I didn't assign it properly, so it's all my fault. Yes? Okay, let's go ahead and do it. All right. Oh, why do I not have that there? Okay. Types of chemical reactions, Tyler DeWitt. And this is on page 22. Okay? If you've already done it, you can, or sorry, 21, page 21. 21. So a compound is made from simpler materials. And for the most part in grade 11, I'm going to give you an element, and you're going to get a compound. Okay? And you'll notice Cl is not Cl2 in sodium chloride. It's just Cl2 when it's on its own.
Grade 12 grad students who have not yet picked up your gown, please come to the office. Any grade 12 students.
These are the easiest ones to predict the products
Please come to the office.
because it's always CO2 and H2O. No matter which hydrocarbon you burn, you are going to get carbon dioxide and you're going to get water. Okay? And we're just about out of time, so we're going to leave it there. You can watch the rest of the video, fill in the blanks. and then do the questions. So that is pages 21 to 24, 25, pages 21 to 25.
Good, just leave it here.
6.2a. Yes, please.
Oh my
Did you
God, love-
finish?
Yeah, I
Okay,
love
good.
this guy.
Right?
God of trust.
Yeah.
I'm his pretty the first bring. Oh, baby.
Oh, thank you.
But then I remembered I already studied 3 times prior.
Yes. Pardon me?
I wasn't able to finish. I have like 4 questions.
Sure.
I was at the,
Right. Do you want to write it tomorrow during class or? Yeah, perfect. Good.
What? I wanted to join that. Like, I don't recommend you. Oh, yeah, we don't do that. And I was like, oh, great. Just not cheese, though.
You would be good. No? Why not?
I'm not talking Here's your, big. Oh, sorry. I got you the next thing. Go to the next page.
Yeah.
You're doing pretty well. You know.
Here, I'll just hold on to it and put it in my drawer of non-finished items. Okay.
Famous last words. Well, I read the test. I'm gonna forget. You don't.
Yeah, boy.
Eric